Hello everyone. So, we will continue with UV protective clothing. In last class we are discussing the different parameters which affect the UV protective performance of textile material. These parameters are raw material related parameters, yarn related parameters, fabric geometry related parameters and technological parameters, and all these parameters if we can manage, if we can manipulate properly, we can develop the fabric with higher UV protection. First we will start with raw material, we will try to understand the raw material. Here if we see that these are classified into three different groups. Polyester is one group, group 2 wool, silk, nylon, and group 3 cotton, rayon. So, these are the cellulosic structure, and polyester is having the structure conjugated aromatic type structure, it is polymer chain. And due to this type of structure of polyester, they are UV protective. So, these are more effective in UV absorption, this type of structure. So, in cellulosic structure there is no double bond in the chemical structure. So, they have less the UV protection here. Sometime the natural pigments, pectins and waxes in natural cellulosic fiber like cotton or jute acts as natural UV absorber. So, the fibers before scouring will have more UV absorbing capacity. Now, coming to the yarn parameters, it has been reported that as the yarn linear density increases, yarn becomes thicker, the UPF increases. So, if we keep the fabric constructional parameter same, the higher yarn linear density, higher text of yarn means it is coarser yarn, that means the mean openness of fabric will reduce, at the same time the effective thickness of the fabric will increase. So, this will effectively increase the UPF value. This figure also shows the similar trend. So, weft count has been increased from 20 to 40. So, in English count, if it increases, that yarn becomes finer. So, as the yarn becomes finer, the UPF value reduces. So, to have higher UPF value, so we have to use the coarser yarn. The pix per centimeter. So, as we increase the pix per centimeter, peak density, we get compact structure keeping all other parameters constant. So, with the increase in pix per centimeter, the UPF increases because effective the openness of fabric reduces. Similarly, fabric tightness. So, as we increase the fabric tightness, the UPF increases. So, to have higher UPF, so we must use coarser yarn with tighter fabric structure, like as cover factor increases, so UPF increases. So, these are the similar trend we get. As far as volume porosity is concerned, with the increase in porosity of fabric, that means the void present in fabric, the UPF value reduces. So, these are for different types of fabrics, types of woven structure. So, for all the fabrics we get similar trend. Fabric mass per unit area, if we increase the mass per unit area, the UV transmittance. So, whatever ultraviolet ray transmission through the fabric takes place, it reduces, that means UPF increases. So, effect of colors, we can see here, the darker the color, the higher is UPF. So, for black color, so UPF is as high as 256. The same fabric undyed, if we use, its UPF is 6. So, if we use the darker color, so for UPF, higher UPF, we have to use the darker color. So, effect of some additives, these are dye, chemicals, pigments, delustrant, optical brightener, UV absorber. The application of these additives will increase the UPF of textile fabric. The techniques to incorporate additives in fabric structures are: addition of additives during fiber and yarn manufacturing. We can incorporate this pigment or delustrant during the fiber manufacturing to get the inherent UV protective fiber, or else we can apply during yarn manufacturing, and also during the wet processing of fabrics we can use these additives on the fabric structure. If we see here UV absorber concentration here, the UV transmittance here for undyed fabric, initially the UV transmittance was very high, but with the increase in concentration of UV absorber, the transmittance decreases gradually, and the similar trend is true for the dyed fabrics also, although the effect is not that significant, because for dyed fabric initially the transmittance percent was very low. Now, we will discuss different research studies to engineer fabric to improve the UV protective performance. First, we will see here a comparative analysis of in vitro UV protection by fabric woven from cotton and bamboo viscose yarn. It is reported in literature that bamboo viscose, they have inherent UV protection performance. To reconfirm this conception, the bamboo viscose fabrics were produced along with the cotton fabric. It is reported that bamboo viscose, they have various positive characteristics: soft and cool feeling, non-irritating, thermoregulating properties, high moisture absorption, breathability, and they are inherently antimicrobial properties, and most importantly they are inherent UV protective properties. So, in the present situation, as we are dealing with UV protective properties, so here the detailed study was carried out to understand the UV protective performance of bamboo viscose fabric made from bamboo viscose fiber and cotton fabrics. So, 3 different counts of cotton and bamboo viscose yarns were taken. So, English count 20, 25, 30, fabrics were produced with ends per inch 50 and peaks per inch was varied 50, 60 and 70. Same parameters were kept for both for cotton and bamboo, thread density, aerial density, cover percent, shrinkage percent and UV protection factor were measured. Now, here if we see the UPF for both for cotton and viscose for different fabrics, yarn count 20, 25, 30, for peak density 50, 60, 70. So, what we have seen here, overall the UPF of viscose is higher than, much higher than the cotton. So, typically the increase is around say 30-40%, even 50% increase is there as compared to cotton. And this fabric specification, yarn count and peak densities are in the loom stage, not at the final stage, and UPF was measured after the finishing of the fabric. It is not in the loom stage fabric, but as reported in earlier literatures, the viscose fabric was giving higher UPF value. Now, to understand the detailed the phenomena, why the viscose is giving higher UPF. So, different studies were carried out. So, here if we see the peak density, this is for cotton and viscose, and cover factor at 50 peak density of fabric in the loom stage. So, cover factors were measured here. Effectively there is no specific trend here, but at lower cover factor, lower peak density, the cover factor of bamboo fiber was higher than cotton, and for higher peak density they are almost same. There is no specific trend. This is for 20s count, 25 count coarser yarn, there is no such trend, but when we talk about the finer yarn, finer weft yarn, this is 25 count and 30s count. So, both warp and weft. So, 25 count and 30s count, the trend, clear trend was observed in case of 30s count. 30s count, it has been observed that the cover factor of bamboo viscose is higher than the cotton for all the peak densities. This has given us one clue why the cover factors are increased, they have increased. So, aerial density has been observed, that aerial density, the fabric mass per unit area for all the conditions, for different yarn count, different peak densities, for all the combinations, it has been observed that the aerial density of viscose, bamboo viscose is always higher than the cotton. Keeping all the parameters same, this increase in aerial density is only due to the shrinkage which is taking place after weaving. So, this table shows clear indication here. This is the warp count. So, fabric shrinkage percent for warp wise direction, for cotton shrinkage is around 7 to say 13%, warp wise bamboo viscose shrinkage is much higher, it is around 20%, 15 to 20%, and weft wise shrinkage is also high, it can go up to say 25% or something, whereas this cotton is around 18 to 20% in this range. So, it has been observed for all the combinations, the viscose, the bamboo viscose fabric is having higher shrinkage. So, that increase in mass per unit area is mainly due to higher shrinkage. Now, to predict the UPF value, we can use either cover as a parameter or mass per unit as a parameter. So, cover means that distance between thread, higher cover means higher protection, that means it will actually obstruct the UV ray to pass through, that we can if we take. So, UPF is taken as y parameter and cover is x as parameter. Okay. So, this is UPF value, x is cover percent. So, we will get this equation y equal to 0.0158 e to the power 0.0671 x. So, this is the equation, exponential equation we get, and here mean absolute percent error is giving 7.41%. This is the error percent. Here predicted model of UPF from cover percent of cotton fabric. Now, predicted model of for bamboo using cotton cover means using the same equation which we have observed for cotton fabric with cover percent as the x parameter. Okay. What we can observe here, here the error percent is increased. Cotton, if we use with the cotton model, the error percent was 7.41%. Same model if we try to use for viscose, the error percent has increased, which means that the cotton model we cannot use for viscose fabric, bamboo viscose, because they behave entirely in different ways. Now, if we use bamboo viscose fiber fabric versus cover, this is the here the bamboo viscose cover percent. So, same fabric if we use the relationship will be here 0.0017 e to the power 0.092 x. This is the equation here if we use the viscose model, viscose cover factor model, and the error percent has reduced to 14.58 if we use viscose model, and in case of cotton model as we have seen the error was 18.15. Still we see the cover factor if we take, still even with the viscose bamboo viscose model the error percent is high. Apart from the cover factor, another parameter which affect directly the UPF, that is mass per unit area. Now, let us take the areal density, that is mass per unit area, and for cotton model, cotton areal density model, this is coming out to be y equal to 1.0476 e to the power 0.0145 x, where x is the areal density of cotton fabric, and here the error percent is 7.24, that is the error. And if we use this areal density of cotton with the bamboo viscose, the error has increased to 8.75, but still this error is much lower than the cover factor. You can see here it is 4.93 when we used the viscose as a model, and using cotton model it is becoming 8.75. So, one can now see that to predict the UPF of fabric, we can use that areal density as independent variable. Now, if we see that areal density for cotton, with cotton model it is 7.24 and area and density of bamboo viscose with bamboo model it is 4.93. Bamboo viscose with its own model, so 4.93. So, it is recommended that we should use their own model, but areal density as independent variable, not the cover factor. So, cover factor gives higher error percent. Now, to extend this study, what we have done here, that UV ray transmission we have measured at different wavelengths, and what we have developed, we have developed fabrics of cotton and the bamboo viscose, this is bamboo viscose cotton, keeping the mass per unit area and cover percent same, exactly same. So, two fabrics were developed. After finishing, the mass per unit area were close to 107 and cover percent was around 84%. In gray stage, we have arranged the ends per inch, peaks per inch in such a fashion that after shrinkage, after washing, the fabric's cover percent becomes 84%. This we have done based on previous experimental result. If we know the shrinkage percent, that we can arrange, we can manipulate the structure. So, effectively cotton and viscose, as far as mass per unit area and cover percent are concerned, they are exactly same, and for that this figure shows there is effectively no change, no distinguishable difference in UV protection properties of cotton and bamboo viscose fiber. So, earlier assumptions were that bamboo viscose gives higher protection, but the present study shows that there is no difference, effectively there is no difference between cotton and bamboo. So, the conclusions are, the fabrics made of 100% bamboo viscose yarn shows higher UPF than 100% cotton fabrics having same yarn count and machine set thread density. This is machine set thread density, not the final thread density. For the same fabric parameters, higher UPF of bamboo viscose fiber fabrics can be attributed to their higher areal density and cover percent, resulting from higher shrinkage. So, UV transmission through cotton and bamboo viscose fabrics having same cover factor and same areal density, they are almost same. So, there is no difference in UV protection properties of cotton and bamboo viscose. So, if we see the protection purpose, so we can use cotton as well as viscose depending on our availability. So, viscose, bamboo viscose does not add to any extra protection. Now, we will see the effects of yarn twist, modified yarn structure and fabric thickness on UV protection of woven fabrics. So, these are the parameters which directly affect the UPF of woven fabrics. First, we will see the yarn twist. Modified yarn structure means here what we have created the hollow structure, and it is compared with the normal yarn, and fabric thickness was by changing the yarn count, yarn linear density, keeping the mass per unit area same. It has reported that higher fabric thickness will give higher protection, but in the present study what we have tried to keep the mass per unit area constant, and we have changed the thickness by changing the yarn linear density. or yarn diameter. First let us see the effect of yarn twist. So, if we change the yarn twist, if we increase the yarn twist, the yarn diameter will reduce and increasing yarn twist will affect the yarn hairiness. So, higher yarn twist will have higher yarn hairiness. So, these two factors indirectly affect the fabric cover and the yarn UV protection. Hairiness also affect the, it scatter the UV rays and ultimately they affect the UPF of fabric. 100% cotton yarn was produced from roving of 0.8 Ne. These are the spinning parameters. 3 yarns were produced with 3 different twist multiplier with yarn count of 20s Ne, 3.6, 3.9 and 4.2 twist multipliers were given. Total 12 fabrics were produced with end density 50 ends per inch, 3 different twist multiplier with 4 different peak density. Total 12 fabrics were produced. Now, if you see the, as we increase the twist multiplier, the yarn diameter reduces. This is obvious because yarns are becoming more and more compact. So, yarn diameter reduces. Now, as we increase the peak density 40, 50, 60, 70, the thickness, effect of thickness is not that significant. So, and for different twist multiplier 3.6, 3.9, 4.2, the thickness effect is, although they are little bit, but not that significant. At very high peak density, very compact fabric, the effect of thickness is visible, but for low peak density it is not that visible. Areal density, as we go on increasing the peak density, areal density increases, but the twist multiplier does not have any effect on areal density. So, areal density there is no effect of twist. Even as far as thickness is concerned, there is no such significant effect of thickness of twist, yarn twist on thickness. So, effectively that the twist multiplier does not have any significant effect of on the UPF of fabric. So, no specific trend has been observed on UPF with increase in twist level. So, twist level, if we try to keep the mass per unit area, ends per inch, peaks per inch constant, this twist level it is not showing any significant trend. The reason can be explained here in the two factors which I have already mentioned. This is at low level of twist and at high level of twist, this is low level of twist. Same yarn, if we increase the twist at higher level, twist has been increased. What happened? The diameter of yarn is d here, here diameter is d, same yarn count. So, the diameter has reduced, but at the same time with the increase in twist the hairiness has increased. Here hairiness was less. So, these two effect, they are basically contradictory effect. Now, if we draw the fabric structure, this fabric is made of low twist state. low twisted, and this is the peak density, say peak density, or this is the end distance or peak distance, whatever may be. So, P 2 peak distance P 1. Now, we are keeping the same ends per inch, peaks per inch. So, here effective opening is more. So, ideally this is high twist, ideally this should, this fabric with high twisted yarn should have transmitted more and more UV ray, but at the same time the second factor comes into picture with hairiness increase. So, this extra hairiness which is actually blocking the pores which has been created due to higher twist will prevent the UV ray to flow through, transmit through, and also it will try to scatter the UV ray. So, that is why these two contradictory factors will actually nullify the effect of yarn twist on the UV transmission. So, for this reason there is no effect was observed, though no specific trends were observed. Now, in the second part it was tried to develop hollow yarn and to see the effect of presence of hollow yarn on the UV protection characteristics of the woven fabrics here. This hollow yarn with greater outer diameter as compared to the yarn with normal yarn of equal count. That means, mass per unit length of yarn, both the yarns are same. So, hollow yarn will have higher diameter, outer diameter. So, d 1 is the diameter, the outer diameter of the hollow yarn, and d 2 is the inner diameter. So, mass per unit length is proportional to that this cross sectional area, and here this is the cross sectional area of the normal yarn. So, effectively d 1 square minus d 2 square equal to d square. So, d 1 square is always higher than d square. So, to keep the same mass per unit area, the two yarns were used, one was hollow yarn, another was normal yarn, and ends per inch and peaks per inch. So, end density and peak density were kept same. So, in that case it has been observed that hollow yarn with higher diameter covers more area than normal yarn. This is the hollow yarn and here is normal yarn, but the fact is that hollow yarn after removal of the core, when it becomes hollow, but during processing yarn gets flattened. So, it further covers the yarn, that inter yarn space, and this core was of PVA yarn, PVA fiber, and after washing in warm water this PVA gets dissolved, leaving the hollow portion, and normal yarn when we press, this does not get that much flattened. So, compressibility of hollow yarn will be higher than the normal yarn. So, hollow yarn will give better yarn flattening as compared to normal yarn, therefore, it will give higher fabric cover. So, that was the idea to improve the UPF value by incorporating the hollow yarn. The materials were used 100% cotton roving and PVA multifilament yarn, so with 20 English count. In the ring spinning process, the core spun yarns were produced with the twist multiplier 4.2 and yarn count, 2 yarn counts were produced, 20s count and core yarn 10s count. So, normal yarn 20s count, core yarn 10s count means here the mixing was that 50-50, 50% core and 50% sheath. Sheath material was cotton. After washing, after removal of the PVA core, this yarn will become 20s. So, both the yarns, hollow yarn and normal yarn, effectively they are 20 English count. This is the manufacturing process. PVA filaments were pre-tensioned and they are fed at the front roller, and staple yarn, staple roving, that is cotton roving was used. It has been drafted, and after front roller during twisting this PVA filaments form the core structure, and here the fabrics were produced, 8 different fabrics were produced. With the plain woven fabric, ends per inch was kept constant for all the fabrics 50. 2 types of yarn, normal yarn and core yarn. Core yarn, here the washing was done after the fabric manufacturing. So, effectively core yarn linear density was 10 Ne was the count. Peak densities were 20, 30, 40 and 50. So, at different peak densities the fabrics were produced. The wet treatment, desizing, scouring and bleaching was done, and during this wet treatment the PVA fibers were dissolved, forming the hollow yarn, and calendering process was done after the wet treatment, which allows the yarns to be flattened, and hollow yarns were observed to be flattened more. If we see the cross section here, these are the core spun yarn, core spun yarns, and this core spun yarns, this portion it is a core, PVA filament core, and after the washing treatment the PVA cores were dissolved and hollow yarns are produced. These are the hollow yarns. Here we can see the voids are there, and if you see the fabric cross section here, the hollow yarns in the weft where flattening takes place. So, during flattening, if you see this hollow yarns, they almost cover the open space between the threads due to flattening, whereas this normal yarn they did not flatten in that extent. So, there are openings present in the fabric structure. The yarn diameter, that is measure axis in the fabric after flattening, normal yarn it is 0.368 after flattening, that the measure axis. The core yarn has become 0.502, although their linear densities are same 20 English count, and these are taken from fabric stage. So, increase in yarn diameter, measure axis diameter, it is 36% increase. So, there is a 36% increase in diameter, So, that is why cover factor is cover percent is always higher than the normal yarn, and the cover percent also increases with the increase in peak density. If we see the aerial density is almost same for both the cases. So, by yarn engineering what we have created different cover factor, but same mass per unit area that is created. So, we wanted to see the effect of mass per unit area is significant or effect of cover factor is significant. Here we can see here that for different peak density, the increase in cover factors, proportion of increase in cover factors are reported here. For lower peak density, the cover factor increases only 2.5% for 20 peak density, that increase from normal yarn to core yarn. But for higher peak density, this increase is around 20%, 19.6% increase. That means, as we go on increasing the peak density, the proportion increase in cover percent increases. So, image of normal yarn and core yarn, this is normal yarn with higher openings, these are the core yarn, these are before flattening. So, at low level of cover, the enhancement of UPF is very small, however, it gets amplified with the increase in cover percent. Now, here if we see again the effect of hairiness will come into picture. So, you have this is low level of cover, and when we talk about the high level of cover, by increasing the peaks per inch, so these are the openings, here the openings are smaller. Now, for normal to core span, there will be increase in cover percent, and due to that the UPF will also increase. But here at higher level of cover, due to flattening there will be increase in cover and UPF will increase, but the presence of hairiness with the open structure, the effect of hairiness will be insignificant. But when the fabrics are compact, that presence of hairiness will have significant impact on the UPF. That is why the UPF increases more during flattening when the cover percent is high. So, here the cover percent is high, the impact is 19%. This impact is mainly due to the hairiness present. Okay. At low cover, most of the UV is transmitted through the pores, and thus the effect of core yarn plays very minor role. At high cover, transmission is low, thus even a small increment of cover leads to further reduction in transmission and significant increase in UPF. So, that is with UV finish, ultraviolet finish treatment, here the enhancement, the increase is much higher than the untreated. So, earlier it was the untreated fiber, untreated fabric, but here this is UV finish treatment. Fabric with hollow yarn structure gives higher UPF in comparison with the fabric with normal yarn. the difference become more prominent at higher cover factor. Also the difference in UPF is amplified after UV finish treatment. So, this is clear here, it is difference is magnified. The UV finish improves the UV absorption by the fiber itself. Thus, the transmission through the yarn becomes non-existent, because the fiber also absorb the UPF. So, the effect of core yarn which leads to higher cover factor gets amplified. So, here also the UV finishing, it helps in the absorption by the fiber. So, whatever flattening took place, it gets amplified when the fibers start absorbing the UV. And our next study will be the effect of fabric thickness keeping the cover factor same. So, that we will discuss in the next class. Till then, thank you.